Welcome back, class. So in this video, we are going to talk about the effect of the reactant concentration on our reaction rates. So in our first video, we talked about general ideas about the rates of chemical reactions. And we mentioned that one of the things that often that can affect the rate of that reaction is the concentration. So by changing the concentration of our reactants, we can change the rate of that reaction. For most reactions, not all reactions, but for a lot of reactions, if we change that concentration, we can change the rate of the rate that reaction occurs. So the way that this is shown, or the equation that this is shown by, is something called the rate law of a reaction. So each reaction has its own unique rate law, right? So the rate, when we talk about rate law, it's not, a uniform mathematical equation, that you might see like the ideal gas law, right? It is a equation that relates the rate of a given reaction to the concentrations of the reactants that we're using. So it's concentration of reactants versus rate. Now, the rate laws are particularly useful when the reverse reaction is negligible, right? So we'll get into this more again as we go through more chapters, but when the equilibrium of the reaction, or when the reaction is very product favored, right? When the forward reaction is much more favored than the reverse reaction. So a couple things to think about, right? The rate of the reaction is directly proportional to the concentration of each reactant raised to some power. And so if we start by looking at very simple reactions, right, where there's one reactant that's generating products, and again, it doesn't matter what the products are because the rate laws only deal with the concentrations of the reactants, not the products. The rate law would take the following form, right? The rate of the reaction would be equal to the concentration, again, in brackets, so the molarity of A raised to some power, which were labeled N. Now, notice there is also the presence of K, and K is a proportionality constant, right, which is called the rate constant. So we have the rate constant of the reaction. So again, N, right, our exponent, is called the order. And so the order of the reaction in terms of A is equal to whatever N is here. Now usually this is an integer value, and it determines how the rate is affected by the concentration. So there's different kinds of effects, right, depending on what that exponent is. Now, that exponent doesn't have to be a whole number, right? It could be a fraction, but most of the reactions that we look at will have whole numbers there. So let's look a little bit more at reaction order. So again, that exponent of each reactant in our rate law is called the order with respect to that reactant. Now, if you have multiple reactants and you add up those exponents, that will give you what's called the overall order of the reaction. So if there's only one reactant, then of course the order of that reactant would be your overall order, be the same. But if you have multiple reactants, like in the rate law here, where you have NO and O2 as your two reactants, right, it would be second order, right? In NO, first order, right? If it's a 1, we don't show it, right? It'd be first order in O2, but the overall order would be third order. Now, when we start talking about rate laws, one of the things that is extremely important, and I will continue to say this over and over again, is that the rate law for a reaction must be determined experimentally. So In other words, what you can't do is just look at the reaction and determine the rate law. The only way to do it is to run experiments, get experimental data, and determine the rate law. Right? There is no way to look at the reaction and the balanced equation, etc., and determine what the rate law is for that reaction. So we can determine a lot of things in the balanced equation, but the kinetics of the reaction is not one of them. Okay, so always keep that in mind. So let's look at a different kind of graph. So in the last section, we looked at concentration versus time, right? And that gave us, our graphs. But concentration versus time is not what we want here. What we actually want is the rate versus concentration, right? Those are the two factors that we're looking at. So again, we're going to use our model reaction here with a single reactant A that makes some products. And what we're going to look here is what we see for three particular orders of A. These are the three most common orders, and so we're going to look at what the graphs look like, or what the behavior looks like when we have these particular orders. So let's say that the order of A is zero order. So if the reaction is zero order, what that means is the reaction is independent of the concentration of A. Because remember, in our rate law, right? So remember our rate law here. If n is 0, right, anything raised to the 0 power is 1. So it doesn't matter what you put for A, right? If you raise it to 0, then it's always going to be 1. And so the rate is going to just be equal to k, essentially. In other words, it's a constant. And that's what we see graphically here when we see zero order, right? We see a straight line. Doesn't matter what the concentration is, the rate is always going to be the same. So, but what if you're what we call first order? So what if n is 1? That means the rate is directly proportional to concentration. So in other words, whatever change we make in the concentration, that effect is shown on the rate. So for example, if I double the concentration, I'll double the rate. Right? So if we think about it, if I have a 1 here, right? Essentially, if you raise something to the first power, right, it's itself. And so if I double A, right, then the effect is going to be to double the rate, right? We're going to have K times A, and so if I double A, then the result doubles. If I triple A, the result triples, etc. So we get what we call a proportional response. Now, if n equals 2, this is what we call second order. Now, as maybe not surprising, right? So if you raise something to the second power, that's a square, right? And so whatever change I make to the concentration, the effect on the rate is going to be the square of that change. And so if I double this concentration, then it's going to be doubled squared, or 2 squared, or we get a 4 times, or a 2 squared effect. So doubling gives me a 2 squared effect, or a quadrupling of the rate. Now, just to show you another example, let's say I tripled it. So I went from 1 to 3. So I'm going to have my 3 squared. I get a 9 times effect, right? So if I triple the concentration, the rate would increase 9-fold. So if something is second order, one thing that we can notice immediately is that, a fairly small change in concentration can have a pretty significant effect on the rate, right? So knowing what the order is can be important when we are trying to affect the rate of the reaction. these are our three most common orders: zero order, first order, second order. And these are the ones that we're going to talk about almost exclusively, and the ones that I'll expect you to be, very familiar with. Okay. So let's look at this a little bit more. Now, this is a lot of the stuff that I just said, but I just wanted to put it out here in a little bit more organized way. So one of the experimental methodologies that we often use when we study kinetics is something called the method of initial rates. And so what this means is we are going to vary the initial concentrations, right? So we vary the starting or the initial concentrations of the reactants, and we see what the effect on the rate is, right? So does it have a zero order effect, a first order effect, a second order effect, right? And so we do multiple experiments using different initial concentrations to get what we call initial rates. And so this is called the method of initial rates, and this is what we do. So, for example, I'm going to run a set of experiments, and I have various initial concentrations, and I see how the rate changes. So if a reaction is truly zero order in A, right, it doesn't matter what this concentration is, the rate will be the same, and we would see data that looks something like this, right? So I vary my concentration, and I see the same rate, so that's going to tell me that it's zero order in A. Now, what if it's first order? What kind of see? So let's say I double it here. So a lot of times we can do this visually. So I had a twofold effect in the concentration, right? I doubled it. So if I look at these first two trials, what happened to the rate? Well, it went from 0.015 to 0.03. It also doubled. Well, this looks like a proportional effect, right? I doubled the concentration, I doubled the rate. That seems like first order. Now, in this particular case, I have another trial that I can use, right? If I use these two examples, I also doubled it, and I see another doubling of the rate. So again, and just emphasizing that first order effect. Now, what if it's second order? What kind of data would I expect? So again, if I look at those same two trials and I doubled it, if it's second order, right, I would expect a squared effect. And so if I see my rate go from 0.015 to 0.06 times 4, right, so it's 2 times. So here I'm clearly seeing a 2 squared or a squared effect, which indicates second order. So this is what we can do if we're given data and we're asked to say, what's the order of A? And then what's the rate law, right? Assuming there's only, this is looking at right now a very simple example of a single reactant. We can oftentimes do that just by looking at the data and seeing the effects. Now, what if we do have multiple reactants? How do we do that? Well, it's just a similar idea, except we're going to have more data, right? So the basic approach experimentally that somebody would use is they would do a set of experiments where we change the initial concentration of one reactant at a time. So this goes back to, experimental design where we change one variable at a time, keep everything else the same. So we change the initial concentration of one reactant at a time, and we look at the effect on the rate. So, for example, if I look at a set of data here, so I ran 4 experiments. if I look at experiments 1 and 2, right, notice I changed NO2 but left CO the same. So we need to be careful here, right? Because, we have to be careful about which two reactants we choose, right? I can't just choose any of them, right? So I might look at this and say, oh, well, okay, I doubled it here, but notice these are also changing, right? Those aren't going to be good because I'm not going to know where the effect comes from. So I have to make sure one of my reactants, or all but the one that I'm looking at, are unchanged. So to look at NO2, reactions 1 and 2 would be the useful ones. So I doubled it. What was the effect on the rate? Well, if I look at this and I say, okay, what was the effect? Well, I can look at that by doing 0.82 divided by 0.0021. Now, it's not maybe exact data, but this is a lot of times what it's going to look like. You're not just going to, may just not be able to look at it and say, oh, it did this change. So we do the division. And we see that it changed by a factor of 3.9. Now, of course, that's approximately 4. So we can make, I think, a pretty good idea that I doubled it here and the rate went up by times 4, or a squared effect, or a second order effect. Now, if you really wanted to sort of test that again or just look at it, you might see that there is 2 other trials, 1 and 4, where I changed NO2, but CO stayed the same. But notice here, I went up by times 4. So what would I expect the rate to do? I would expect the rate, if it's second order, to go up by 4 squared, or 16 times. And if I look at 0.0021 to 0.033, and I did that, 0.033 divided by 0.0021, you should prove to yourself that you get about a 16 times effect, 15.7. So we're seeing that borne out, that second order effect. But what about looking at CO? So right now I can say, oh, okay, my rate law is going to be the rate. We're always going to have a rate constant. NO2 here is going to be second order. But what about CO? Well, let's first pick out which trials we're going to use. So remember, we have to look at something where NO2 stays the same. So the only 2 that I see the same are going to be 2 and 3. Right? Okay. So I'm going to look at trials 2 and 3. So I doubled it here. What happened to the rate? Oh, it didn't change. So remember, if the rate didn't change, that's a 0 order effect. So we can conclude that it is CO that has a 0 order effect. So our rate law here is going to be the rate equals K times concentration of NO2 to the second order, or squared, times concentration of CO raised to the 0 order, or raised to the 0. Now you might simplify this. It's okay if you don't, but a lot of times you might see this simplified, where they would just drop out the CO because, of course, raised to the 0 power, it becomes 1. But if we want to leave it here just to emphasize the fact that it's 0 order, nothing wrong with that. We just need to know that if we raise, no matter what it is, we plug it in here, it's going to be 1. So the idea is, by looking at this kind of data, our goal here is to determine the rate law. Now, one of the things that we often do here, and we'll do an example problem, and I'll post some other videos giving more example problems, is this is typically the first step that we do with initial rates. Oftentimes, as a follow-up, right, the idea is, okay, what's the rate law? But the second thing is to determine the rate constant K. So how would we go about determining K? Well, let's just look at it here. So we're going to pick any reaction here. It doesn't matter which one because it is a rate constant. It should be exactly the same. So let's just pick number 1. So I have my rate equals K times the concentration of NO2 is 0.1 squared. Concentration of CO, 0.1 raised to the 0 power. So now it's just a matter of mathematically solving it, right? So I know for trial 1, my rate is 0.0021. So I have 0.0021 equals K 0.1 squared, right? So if I do 0.1 times 0.1, I get 0.01. Now 0.1 to 0 is 1, so we don't need to worry about that. So K simply becomes K simply becomes 0.0021 divided by 0.01 equals 0.21 equals K. So my rate constant equals 0.21. So that's typically what you would do with initial rate data, right? Is we often use it to calculate the rate constant. And so now you know every part of this equation. So now you could take any concentrations and figure out what the rate would be once you know the rate constant. And if you pick another trial, 2, 3, 4, 5, do the same thing. You should come up with the same rate constant within rounding errors. All right, so that sort of wraps up our discussion of rate laws. In the next video, we're going to talk about something called integrated rate laws, where we look at the effect of concentration over time, right? How does the concentration change over time?